Welcome to this section. In this section, we shall get into the modeling of our automatic speech recognition system. Our very first layers will take in the spectrogram, as you can see right here. So we shall have some Conv 2D layers in the beginning for our network, followed by some Conv 1D layers. And then finally, we shall use a CTC loss. CTC stands for Connectionist Temporal Classification. The CTC loss is employed in problems where the inputs and the outputs vary in length. From our data set, we've seen that our inputs can vary from, say, 1 second to 10 seconds. And also, the CTC is used when we don't have an accurate or well-defined mapping between the inputs and the outputs. Now let's explain that. Suppose we have this input right here and that we want to pronounce the word happy. So someone may say happy. So the ha could go right up to there. So suppose we're starting from here, we could have happy. So the P starts from this. Now another person could say happy. So the P starts from this position right up to the end. Now, in this kind of situation, we see that even though we have the same output right here, happy, we don't have the same mapping between the input, which was given to us, and the output. And this depends on the person who is actually recording the audio. So, in such situations, we use the CTC loss. Apart from speech recognition, another common example is that of text recognition. Now, suppose we were writing the word happy, we write happy. So suppose person 1 writes happy like this, happy like this, and then our output is this word happy. So we're actually having a model which takes in written text and then outputs this corresponding characters which are found in this written text. Now this may be an example of the word happy, or the way one person writes happy. Another person could write it like this. So right here you see that this H and A occupy 3 positions with respect to this first. You see right here already. So here we have 3 positions occupied by just 2 positions for person 1. So let's suppose this person 1 and person 2. So this tells us already that there is no direct mapping or known precise and accurate mapping between the inputs and the outputs. Now that said, suppose we have this input and then it outputs the word latter. We could build our model such that we have this kind of outputs. As you can see here, we have latter, we have latter, we have latter, and then we expect that if we have this kind of outputs after the prediction, then we should be able to say join all the A's. Like if we have this A, we join it to form one A, this T's to form one T, E, R. So we have this now. But the problem with this is that it generates this word later, which is different from the word latter. So this clearly isn't the kind of model we would like to be building. Now, the way the CTC algorithm solves this is by introducing this extra token in our vocabulary called the link. So suppose we want to output this, we have this different possibilities. Suppose we have a vocabulary made of 6 words, L, A, T, E, R, and then the link. Now, we want to predict that we have 8 different positions in our sequence length. So for each of this position, we have to predict which of this corresponds. Now if we want to have this, we may have different options, like say we could have L, that's if we pick this, and then the next we pick this, and then the next we pick this, and then the next if we pick the link, the next if we pick T, the next if we pick E, the next if we pick R, the next we pick R. So basically they are just those probabilities that the maximum, we're picking out the characters or the tokens with the maximum probability at each step in the sequence length. And this for this example gives us this. Now we see that thanks to the link token, what we have here is L, A, T, And since this link token is found here, we don't have to join this double T as we were doing previously. Like in this case, we'll have to join this from one T. Now we have the link token, we have T and this other T separate. And then we have E, and then here we join this R because we don't have any link token between them. So this is actually a valid output as compared to this output we got right here. Then let's check now some other outputs. Suppose we have this output L, we pick this, next is this, next is this, next this, and then we have the link, then we have T, then we have E, then we have R. Now this is gonna give us LAT. With a link, we are gonna have LAT TER. So this is actually a valid token, or rather a valid output. Now we go to the next, we have LAT. Now we have the link ER. We see that this gives us LATER. This gives us the word later instead of the word ladder. So this is an invalid output. We go to the next, we have LATTEER. Mixing all of this gives us ladder, which is a valid output because this is our target output and these are the predicted outputs right here. Next we have A. Clearly from this we don't start with L, so this is an invalid output. And then this we have LATTER. It gives us ladder, so this is a valid output. So what we'll do is with the CTC loss, for every step in our sequence length, instead of just coming here and saying we take out the token with the highest probability, the token with the highest probability, this token with the highest probability, this token with the highest probability, and so on and so forth right up to this, what we'll do is we have all this list of different paths that are starting from this to the end. So we could go this, or we could go LA T link T E R R, just like with this first example right here. So we go through all this list of different possibilities, and then we maximize, or we take the link, or we take the path which has the highest probability score at the end after summing all the probabilities throughout the path. And that's how the CTC algorithm minimizes the loss between the paths with the highest probability of occurrence and the target output. And the concept of the valid and invalid paths, you can see the invalid paths are in white, the valid paths are in orange. This concept actually permits us select the paths we're working from the beginning right up to the end, as this prevents us from picking up paths which will not be able to, or wouldn't generate the output, like this one for example. If we were to go LAT link ER, at the end of the day, even if this gives us the value with the highest probability, it's going to be taken off. It's not going to be considered when calculating the loss because it doesn't give us the output, or it doesn't lead to the target output. So only these paths which are valid are considered when making the CTC loss calculation. Also notice that unlike other loss functions where we expect the output prediction by the model, like in this case, to have the same length as that of the target output, in this case we have this output by the model with a sequence length of 8. We have 1 2 3 4 5 6 7 8 positions, whereas the target has just 6 positions. And this is possible because we are using the fact that whenever we have our output, we could join this, like if we have this A's like this, we could join this to form one A. Also, we use the fact that we have this link token which separates joint letters, like in the case where we have double T like this, we could use a link to separate this T from this T. And so with this, we have now this outputs which have sequence lengths which may not be exactly the same as that of the target, and this suits the kind of problem we're trying to solve, wherein the inputs and the outputs are not always of the same length. Now building the code for our model, we have this. we start with a conv 2D layers right here, but before that we have the normalization layer, which is this. We have the input, then after this conv 2D layer we follow it with another conv 2D layer. We have the max pool layer. We reshape so that it could pass through this conv 1D layer, and then finally we have the softmax layer. So we could look at this model summary right here. There we go. So we leave from this input to this output. Notice that this here permits us to get a sequence length of 192, and since we have this vocabulary size of 32, we have this output right here. So for each of the 192 positions, we shall be predicting which of the characters in our vocabulary actually belong to that position. So that's it for our model. We now define the CTC loss right here. We have this. We taken the true, that's the target Y, and then here we have the predicted Y by the model. Then we have this TensorFlow.keras, the backend CTC batch cost function, which takes in the Y target and then the Y predicted by the model. Also note that it takes in the length of the target of the input, that's of the target, and then the length of the predicted. But this is actually the predicted length right here, and this is the target length. To obtain the predicted length, we have to get the shape of the predicted output right here. So we have this TF, the shape of the Y pred. We take the first dimension, which will correspond to 192, and then for the target we have the first dimension of the target output, which actually varies. So that's one of the reasons, or that's the reason why we have to actually input this right here, because the fact that we have this target output dimension which vary simply means that when calculating the loss, we need to know the length of a given output. So this is the Y true, which could have dimension. So comparing with this, we supposing we have in this, the known year stands for the batch dimension. So we could have this, we could have 158, we could have, then we have this. Another could be, let's take this, another output could be 131 or 110, another could be just 15, for example. So these are the kind of outputs we have, whereas our predicted output is fixed, as we could see right here. We modify this, we have instead of true length. So this is our true length, and then that's it. Now also note that since this loss could take in different batches, and that for a given batch we may have varying lengths, because we suppose that a given batch must not always have values with the same length. What we'll do now is we're going to define this in terms of batches. So we have the pred length, we get the batch size times TF the ones, which we define right here. So with this now we are able to obtain the new pred length, such that for each of those batches we have the length, since we now define this new tensor which takes in the prediction lengths for each batch. And then for the target length we have the lengths for each batch right here. Now that done, we just define the batch size. The batch size is equals this shape of the Y pred or the Y true, but the 0 dimension right here. So that's it. So that's good. That's our CTC loss, which has been defined. The next step is we compile the model, as you can see right here, and then we go ahead and train it. So we have this, we run it, we have an error. We look at this right here. We have this has type float 32 that doesn't match the type int of the arguments. We look at that carefully. We'll see that this is where we have that error, and that's simply because this TF.1s is a float. So right here we have this. We need to specify that the D type is in 32. So that's it. We specify as D type as in 32. Run it again. And that's fine. We have this training now correctly. After training for several epochs, we have the following results. You can see we left from 563, now gone down to this. We could now test our model on some data from our training set. Basically, we've trained this on just 2 inputs, so we've just overfit on this, so we could test it and see how well it performs on this overfitted data. For testing our model, we have this. We're taking the text, that's the actual audio file name. We have the path. We get the spectrogram. We pass this into the model. We have the argmax for each element in our sequence length, and then for every I in our output, we convert this into the vocabulary. So once we have this, because if we print out this right here, we have this. So basically we need to convert this into our vocabulary. So once we have this, now we just simply like this, we just simply have this. So for each of this we have T, H, E, Y. That's for the first 4 positions, and then right up to the end. We notice that we have this links. That's because right here we had modified this to suit what we had in the slides. So normally we could take this off. We just added the links, and then that was it. We left and we were now at 33 instead of 32. Nonetheless, we could take this pad off because that isn't useful. We're just trying to make sure it matches up with what we had previously in the slides. So once we have this is the kind of output we obtain. But it should be noted that we could also use an inbuilt function by TensorFlow to decode our outputs, as this is not the best kind of output we could get, since it doesn't take into consideration the way the CTC loss was computed. That said, we're going to define a new decode function which now uses this inbuilt TensorFlow CTC decode function. So the way this works is we just put in the output, or first of all we get the output from this. That's we do the model predict, we have the argmax, then we have our output. Now once we have this output, we convert it into its 1-hot notation. So we have this 1-hot conversion right here. Once we convert it, we pass it into this CTC decode function. We specify the input length, obviously, because as we may have different batches, or we may want to decode for several batches. So we have this. Note that this time around we just have the dimension of this is just the batch size, so it's not a batch size with say a 1 like it was with a loss. So that's what we have here. Then once we're done with this part, we multiply with a prediction length, which we get from this. As we did in the loss, we have the batch size gotten from this. We pass it into this. Then we specify that we're going to use a greedy algorithm to be able to do this decoding. Now once we have this, we take in this values at a 0, 0 index. Then from this we have the output. We just repeat the same process we went through right here, and then we have that. So the main difference we have with this tool is that the decoding is done using this after obtaining the outputs. So we could run this, and there we go. We now have our decoded output, which doesn't include the links in between the words, and that's because this CTC decoder understands how the initial CTC encoding was done. Now once we have this output, the next thing we could do is to compare it with the exact output which we have expected. So we're using the audio text dictionary which we had defined previously. We have this text string from here, and then we get in this exact output right here. So we have this, which could be seen as almost the same as what we have here. To have better results, suffice to train this for more epochs, and then also to make sure we don't just overfit our data, we could train now on the full data set and even increase our data set if possible, so that we don't overfit our model.